Have you ever looked at one of those ridiculously expensive, super thick audio cables and wondered, is it really worth it? For decades, the common wisdom has been pretty clear. Thicker wire is always better. But what if there's a little-known theory, one that's grounded in some serious physics, that turns that entire idea completely on its head? Okay, let's dive into this.
So this is the question, right? It's at the heart of one of the longest-running debates in the entire audio world. We're all taught to think of electricity like water flowing through a pipe. A bigger pipe lets more water through with less resistance. Seems totally logical. But when we're talking about the tiny, delicate nuances of sound, that simple model might just be leading us completely astray.
So on one side, you have the common view, straight out of every basic electronics textbook. Thicker wire means less resistance. Simple. But on the other side, you've got this persistent claim from the audiophile world that says something totally counterintuitive, that thin, solid-core wires can actually sound better. They're the ones saying that the whole water pipe analogy is just plain wrong for high-fidelity audio. To really see why they might be onto something, we need a much deeper model.
Yeah, that water pipe model is a great starting point, but it misses a huge piece of the puzzle. To really get what's happening inside an audio cable, we have to go way deeper, beyond just simple resistance, and start looking at the real physics of how a signal actually travels.
So where did this radical idea even come from? Well, this quote points us right to the source. Back in 1985, a physicist named Malcolm Hawksford decided to tackle this question, not with just listening tests, but by going back to the fundamental principles of electromagnetism, the ones laid down by the legendary James Clerk Maxwell. He wasn't just guessing, he was doing the hard math.
And this right here is the first major shift in thinking. A cable isn't just a pipe for electrons. No, it's a waveguide for an electromagnetic wave. According to Maxwell's equations, the vast majority of the signal's energy doesn't even travel in the wire itself. It travels in the dielectric, that's just the fancy term for the insulation, or even the empty space between the wires. Think of the wires as just rails, guiding the real energy that's flying through the space around them.
Okay, so this leads to a pretty crucial question. If most of the energy is flying along in the space between the wires, what in the world is happening inside the actual copper? Well, the answer to that is the key to this whole mystery.
So, Hawksford's model shows that the energy actually splits and takes two different paths. First, you've got the main wave. This is your music, your signal, and it's zipping through that dielectric space at almost the speed of light. But second, and this is where the trouble begins, a tiny bit of that energy spills over and creates what he calls a loss wave that moves into the copper wire itself. And when I say trouble, I mean there is a shocking, almost unbelievable difference in speed. I mean, look at this. The main signal is moving at the speed of light, but that loss wave inside the copper, at a pretty normal audio frequency of 1 kilohertz, it's crawling along at about 13 meters per second. That's actually slower than the speed of sound in air. So one part of your signal is a fighter jet and the other is taking a slow walk in the park.
So what's the big deal? Well, this enormous speed difference creates a really weird problem because that loss wave is so incredibly slow to move through the conductor and then dissipate. The wire essentially remembers a small part of the signal that just passed through it. The conductor itself develops a kind of short-term memory.
So how deep does this weird memory effect go? Well, that depends entirely on a concept called skin depth. It's basically the distance that an electromagnetic wave can push its way into the wire before it fizzles out. And here's the critical part. That depth isn't constant. It changes dramatically depending on the frequency of the sound.
And this table just makes it crystal clear. You see, for low bass frequencies like 100 Hz, the skin depth is over 6 millimeters deep. But when you get up to high treble frequencies, say 20,000 Hz, it's less than half a millimeter. This means different parts of your music, the bass, the mids, the treble, are all interacting with different amounts of the copper conductor.
And here's Hawksford himself, describing what happens next. He says this memory influences the transient behavior of the signal. The sharp, sudden sounds like the crack of a snare drum or the pluck of a guitar string, by time smearing them.
So what does time smear even sound like? Well, imagine a sharp clap in a small, quiet room. It's crisp, right? Now imagine that same clap in a huge, empty cathedral. The echo and the reverberation blur the sharp start and stop of that sound. This slow loss wave does something very similar, just on a microscopic scale. It releases its stored energy just a fraction of a second late, and that blurs the fine details of the music. And we can even put a number on it.
At 1 kilohertz, it takes that loss wave, about 0.159 milliseconds, to travel through the skin depth. Now, that might seem incredibly fast, right? But in the world of high-fidelity audio, where our ears can perceive tiny timing differences that create stereo imaging and realism, that is a significant delay. It's enough to damage the integrity of the sound.
So let's bring this all together and apply the theory. With a thick wire, its diameter is way bigger than the skin depth for most audio frequencies, so it provides this big reservoir where that slow loss wave can store its energy, and that results in that memory effect and time smear. But with a thin, solid core wire, one whose diameter is actually less than the skin depth, there's almost nowhere for that slow wave to go. The conductor effectively loses its memory and starts to behave like a simple, pure resistor, which is what we want.
So what about those super common, flexible, stranded wires that everybody uses? Well, Hoxford is pretty blunt about it. From the perspective of this model, they're a poor choice. That slow loss wave has to navigate a chaotic mess of individual strands and tiny air gaps, creating countless little disruptions and reflections, making the time smearing problem even worse.
All right, so what are the big takeaways from all this? First, a cable isn't a pipe, it's a waveguide. Second, there's this slow loss wave inside the copper that creates a memory effect. Third, this memory blurs or smears the signal in time, and that's especially bad for sharp, transient sounds. Thick wires act as a big reservoir for this problem, while really thin, solid wires can basically eliminate it, which helps preserve the timing and the clarity of your music.
You know, this whole theory really shows that even the simplest, most basic component in an audio system, just a piece of wire, is governed by some surprisingly complex physics. It kind of makes you wonder, if we've been thinking about something as simple as a cable all wrong for so long, what other hidden physics, what other subtle effects are out there shaping the very nature of what we hear?